Hey, howdy everyone. So in this video, I'm going to demonstrate how fetch unit of y86 sequential processor works. Okay, so in the previous video, we discussed about how to implement fetch unit. Okay, so you may remember this note, like we fetch first 6 bytes using PC value for a single instruction, and then we output these things like icode, ifun, ra, rb, velc, and velp, and then update PC value using velp. Okay, so we discussed about it, and then today I'm going to demonstrate how it works, and then how you maybe maybe you can refer this, and it shouldn't be exactly same. Depending on your design, it will be different, but output must be same. So here we will more focus on like something like clock, which didn't talk about it, and it is actually challenging thing while you are implementing this. Okay, so okay, let me describe overall circuit of this, and definitely I won't show you detailed logic, but this is just exactly same thing or part of the figure here, and I just make fetch unit around here, and then I have a PC increment here, and also PC block in here, and new PC block in here. Even though it is big box, it doesn't do anything. So I can show you this one because it's nothing. So just it takes a value, VLP as an input, and then output directly connected to the output. So later we will fill this out. Okay, good. But you have to implement fetch unit, PC increment, and PC. Okay. Okay, let me go to this, and so here the fetch unit in the logisim is around this one. So it includes memory, ROM or RAM, and then it has some register to store a single instruction. And then it has an extra logic to produce outputs like data and signal, control signal. Okay. So like when you hover over this output, then you can see, okay, this is icode, and then second is ifun, ra, rb, and velc, and then it takes PC as an input, and also it outputs need velc and need regs, and it goes to the PC increment. Okay, and it outputs the PC increments outputs velc, velp, and also it takes PC. And like I said in the previous video, PC increments just implement this equation simply. Okay. And then to verify our this implementation, I just attached many probe module. Then it actually the snoops this wire to see the input PC value, and then also So this probe read this wire, and also there are many probes to read I code, iPhone, RA, RB, VLC, and what's that? VLP as well. All right. And then what should be our input program? So I'm going to use this program, this machine code as a what's that? Input test program. And we don't have to know about what it does. We just know, okay, we should fetch one instruction at a time. Like after we fetch, so after we read one instruction, then we must see the correct information on correct output of fetch unit, and then we should see the correct updated PC value around here. So input to the fetch unit. Okay, and depending on your design, so maybe you so some part will be different. Like this part could be different with your implementation, but the thing is, the next PC, the PC value going to the fetch unit must be same, I think. Okay, so then before we run this machine, we have to load this machine binary code to the Logisim. But like I told you before in the lab, so you need to come up with some translator to, where is it? I think where is it? Sorry, it's in the Linux server. Sorry, let me go to the quickly. And my example. Okay. Sorry. It's in the same place. I'm really sorry. It's in my laptop. Lab 6 project, my design. Okay. All right. So this file is the input to the Logisim, and this is equivalent to this file in terms of contents. So here it starts with first machine code, which is 3040600000. And it has also 40 F0 46 000000, and then it starts second. Right? So you need to make an automated tool or translator to get this file. Okay. So I already uploaded. Let me double check whether I uploaded that or not. Okay, I did. So then we can start our process and then see. Okay, let me resize this terminal so that we see both screen. Okay, good. So let me tell you one detail of my implementation. So in the fetch unit, in the instruction memory, I use 8-bit data width. So to read 6 bytes, I have to tick, I need 6 clock cycles to read entire data. Okay. Where is it? It's okay. So let me reset the simulation, and then I will manually control this clock to see the detail changes. Okay. So I'm going to click, I'm going to make 6 cycles and then see the situation, status of this processor. 1, 2, 3, 4, 5, 6. Okay, good. Did you notice something changed here after 6? Okay. So what we fetched, so we should fetch this machine code from PC 0, and then next PC should be 006. And then like output of fetch unit should produce correct the information. Okay, let's take a look at the PC. So the PC, next PC is this one, right? So this is 16 bits. So then how do we read? Like in hexa number, we break this binary into 4 bits like this. And then this is 0, 0, 0, and 6. Okay, good. So next PC value, next instruction address is 0006, and it is same with this code. And then what about this? Okay, so maybe I'm using same instruction that we played in the previous video. So so you can study how to decode this machine code, and then you can figure out what should be I code, iPhone, blah, blah, blah. Okay, so first we read first byte, first 4 bit, which is 3, and it should be I code. Okay, this is correct. 0011 is 3, and then second hexa digit is fun. This is 0000. Okay, and then we know the I code 3 is IR move instruction. So what is the format of this IR move instruction? So IR move L. Then first we have immediate value. Sorry, I'm writing a format of this instruction. So in the IR in the machine code, second part will be what? Second 4 bit will be just F. So when you go to the instruction format, let me go to there for IR move instruction. Third 4 bit or third hexa digit is F because we don't use RA register. Okay, it's good. Why? The place of RA, output of RA is 1111, which is just F. Okay, it is correct. And then second, next 4 bit or next one hexa digit indicates RB register ID. And here in a machine code, it is 0. RB is also 0. Okay, by the way, register ID EA0000 is EAX. Cool, good. And then regarding VLC, so this RI move register includes constant value, which is 46000000 here. This one should be in the VLC here. Okay, so let's read this value. So like I did, we break this into 4 bits and then read one by one. So this 0, 0, 0, 0, 0, 0, and 4, 6 in hexa notation. Okay, this is 0, 0, 0, 0, 0, 0, 4, 6, but it's not same, but I already make it exact constant value because the value in this machine code is stored as a little endian using little endian. So I already calculated correct value, but it is easy. You just rewire them in the logic in the fetch unit. Okay, good. So so after reading a first instruction, we checked next PC value and then produced data and control signal from fetch unit. And then yeah, actually this value, next piece value is updated by piece increment along with these 3 inputs. And then it goes to a new PC, and actually it is directly connected with output because we don't have other implementation. So we just directly connect, and then it goes back to PC module, and then goes to the fetch unit. Okay. So we checked this hardware logic with first machine code. And then next, I'm going to check only PC values, whether it fetches, it updates correct PC, which points to the next instruction. Okay. So to fetch for fetch unit, it needs 6 cycles to read 1 instruction and then compute. Okay, let me click 6 times. 1, 2, 3, 4, 5, 6. Okay, and then the next instruction should be 00C. Is it 00C? Yes. 0, 0, 0, and C. This is C. Good. Now what about next? Okay. Let's click on 6 more. 1, 2, 3, 4, 5, 6. Okay, it is updated. Then what is the next PC value? It is 1, 2. Okay, this is 1 and 2. Great. And then one more. I'm going to run until here. Okay, so now we are here. So we didn't fetch this instruction yet. So we are going to fetch it now. Okay, then 1, 2, 3, 4, 5, 6. Okay, and it is 1 and 8. Okay, great. Next PC must be 1, 8. Good. Then let's fetch next instruction. 1, 2, 3, 4, 5, 6. Okay. So next is 1 and E. 1110 is E in hexa. Okay, good. Next is 1E. Good. And let's fetch next instruction. 1, 2, 3, 4, 5, 6. Then what is this value? 2 and 4. So next is 2 and 4. All right, it's correct. It's going well. So let's fetch one more and then we are done. Okay. So far we just fetched 6 bytes long instructions, but next is 2 byte long instruction. Okay. So let's fetch, but still we have to wait 6 cycles. 1, 2, 3, 4, 5, 6. Okay, good. So then next PC is 2 and 6. Okay, good. Next PC is 2 and 6. Okay, so you can, so after you make your own processor, you can, what's that? You can test your processor using this like example machine code, right? So yeah, and then once you make this work correctly, then we can move on to the next stage, which is decoding stage. But if you don't have this, then actually you cannot. Even though you implement decoding unit, you cannot actually make it run like this because this is kind of a baseline of your processor. So that's why we make this in the first week. Okay. Here, let me share my experience while I'm implementing this thing. So I think there's nothing new in terms of designing logic gates, but which means you can use whatever you have learned in the lecture and the lab, right? So when you design a combinational logic, so you can come up with a truth table and a Boolean equation, and then you just convert it to the logic gates, right? And then if you have, so let's say, to read 6-byte instruction using 8-bit data width, then we need to read, we need to generate control signal 6 times with different address. Then maybe you can use a counter. And then, so then for every time you can update the address value, and then read 1 byte at a time. And then after 6, then your counter should be reset to 0, and then fetch, and then PC value will be updated. Okay, here what I'm saying is, see, so PC value is going to keep going to this way, right? But in the middle, okay, let me show you from this thing again slowly, and then show you one thing. So I just reset this simulation, and then PC is 0. It points to the first instruction. So let me click 1, 2, 3, 4, 5. See 5. But I need to click one more, but the thing is, see here, PC value is already updated, but it's not correct. It is correct update, but we didn't. We already calculated this PC value, but we need to fetch one more byte for val C, right? We need to read one more byte for constant value, but if this value directly go to fetch unit, then we will fetch some other address, the data in other address. But as you can see, still this wire, this wire has value 0, which is the address of the first instruction. And then we just +1 and +2 and +3 to read, to come up with the correct address for 6 bytes instruction, right? Then how do I do this? I have something in the PC, and then until during the 6 cycles, even though there is a new PC coming in, we don't output this updated one. It keeps outputting the previous PC, and then after 6 cycles, this PC will start outputting updated PC. Okay, so this is the one common mistake, or something that makes you confused, or make you hard to debug your circuit. Yeah, once you figure this out easily, then the other things should be fine. Okay, so we will. So I'll see you on the next video. Thank you.